start? Okay.
Yes, please.
Okay, hey, so this is a winner presentation of the second place solution for IceCube challenge. The agenda is really simple. We'll give you some background about us, summary of our solution. Then we will go through each steps. We'll talk about data. We'll talk about training methods. We'll talk about something interesting we find, and also at the end we will give you a kind of a simple model that can outperform, the baselines. Okay, so background. So my name is Habib. I never done physics. My background is in biology, in structural biology. Yeah, so I did PhD in Switzerland, and yeah, right now I'm in US, and I work for a startup in San Francisco where I am a machine learning lead. Then I have my amazing teammate. He's Maxim. He is related somehow to physics. He has a PhD in applied physics from University of Virginia. Right now, he also a senior research scientist in computer vision at Blue Halo. So both of us kind of regularly compete in Kaggle. We have, yeah, each of us has like more than 30 competitions. Before competing, solving this IceCube challenge, we kind of worked together on a challenge before. It was detecting gravitational waves. So therefore we know each other from a previous challenge. So then we both started independently working on IceCube challenge, and we saw each other on the leaderboard, and we kind of reached out and we started talking, and we realized that this challenge is, the problem is really well suited for kind of a transformer architecture. And then, we basically start experimenting with transformers. So between me and him, we kind of run, I don't know, approximately 200 experiments. Like I would say 90% were failures. Some of them were successful. And then we ended up at the second place. So let me tell you a little bit about of kind of summary, a big overview of our solution. Basically, our network or our architecture or our approach can be divided into two blocks. One is an encoder block, and second is a decoder block. So for the decoder, we use a transformer, and for encoder here, we have two kind of main things. You can encode, so we're given 1, 2, 3, 4, 5, 6 features, right? So XYZ, it's a detector location. Then we have a time of detection. Then there is charge. And then we also have auxiliary. In order to encode this feature, we can use a GraphNet, which basically, I guess it's organizer baseline. There are some modifications. We're going to talk about them later. So this step is optional. Then our main thing is that we use Fourier encoder layer. Again, we have a separate slide where we go in much more details what exactly happening in this Fourier encoder layer. Then what happens is that we also have this layer. It's called relative space-time interval bias. When we encode this feature, and if you have a GraphNet encoder, we also extract the feature from here. They can get concatenated, and then we feed to several transformer blocks. And one thing which we add here is a class token. It's basically a parameter which used very commonly in transformers, and this layer is kind of responsible for pulling. So we use class token to pull the features and to finally calculate the direction. So each of these components, when we were kind of running these experiments, each of these component had some kind of contribution to our final score, right? So the biggest kind of contribution, or we noticed, was the Fourier encoder. So it's this layer, basically encoding the features using Fourier encoder. It gives out approximately 200 base point improvement. Then if we replace transformer, or if we replace graph neural network with the transformer and with the relative change spice interval bias, it gives you approximately 140 base pair improvement. One trick we did is that during the training, we trained on fixed length. So for example, we will train for 192 events. And during inference, we were running inference as much more detectors. I think 512 or even up to 768. Again, one more thing that if you scale the transformer, the decoder from T to B size, so basically, I forgot T stands for what, but basically, it's, I think tiny to base size, right? So yeah, you will get 60 base pair improvement. And again, using computational metric as a loss, you can get up to 55 base point improvement. And again, tiny improvement if you kind of assemble multiple models. There's nothing about tools special. We use PyTorch and Jupyter notebooks. This is our inference, our models, which we submitted on the Kaggle. They approximately can run 1 million samples for 3 minutes. Per 3 minutes, training was done on our local setup. So Maxime has 490s, and I have two A6000 NVIDIA GPUs. And I think that's it. So Maxime, you want to kind of continue?
I will continue this presentation. First, I will talk about data processing. Organizers have provided us quite large training set, so it was a little bit difficult to handle. And so it was very important at the beginning to build an effective pipeline and perform fast experiments. So our data pipeline consists of the following things. First, we do caching the selected data chunks to minimize the computational cost of data reading and processing. Next, we use chunk-based random sampling for effective use of caching. So during training, we first randomly sample a particular file and then sample all events from this file and go to the next file. And finally, it is length-matched data sampling. Sampling batches with approximately equal lengths. So we minimize the computational overhead introduced by processing of padding tokens when the batch is truncated at the longest sequence. Use of length-matched data sampling has drastically improved the computational speed and enabled us using the sequence lengths of 194 for training and 768 at inference without a noticeable increase of the inference time. Next slide. And next I will talk about the model. First, the question is, why did we choose transformers? Graph neural networks have limitations in particular areas. First, they mainly function at the local level, performing updates based on neighboring nodes. Meanwhile, the model is asked to predict the global quantity, such as the direct direction. To minimize this local versus global mismatch, one can consider dynamic age building. However, it falls short in comparison to multi-head self-attention, which in addition has gradient feedback and also is not limited to the specific number of neighbors. Finally, from first side, it may seem that graph neural networks should be more effective than transformers because they consider only a small, very limited number of neighbors. However, in reality, it appears that graph neural networks are slower because of the extensive use of sparse operations and data rearrangement in comparison to transformers, which utilize highly optimized dense tensor operations. For example, the organizer's baseline with 4 GraphNet blocks and 100.4 million parameters has approximately the same computational cost as 16 block transformer with 7.4 million parameters. So we decided to go with transformers in this competition. Could you go next slide?
Mm-hmm.
And next, I will go through specific parts of the model one by one. I will start with Fourier encoder, which gives the largest boost of the performance. It is very important to convert the continuous input variables into the format suitable for transformer before processing them. We use Fourier encoding, which is commonly used in language models to describe position of tokens in the sequence. It can be viewed as soft digitizing of the input variable into codes defined by Fourier frequencies, which are ranged from 1 to 1 over 10,000. And we applied this encoding to all continuous variables. However, there is one important trick here, is that the variables should be not scaled to the commonly used 0 to 1 range or unit node, but instead it should be scaled to the range with the maximum value of approximately 10,000 to maximize the resolution of this soft discretization. Could you go next slide? Another component of our solution is relative space-time interval bias. Special theory of relativity has such quantity which is called space-time interval. It is approximately equal to 0 for particles moving with a speed close to the speed of light. What is practically used from this is that all detection caused by the same neutrino should have approximately 0 space-time interval between them. By computing the space-time interval between all detections in a given event, we can easily distinguish detections caused by the same neutrino and the noise. And this space-time interval can be naturally added to transformer as a relative bias. So the transformer is able to group detections based on the source event. Could you go next?
Yes. Okay, so, all right, so, we had already pretty good solution. It was, kind of high on the leaderboard. And one thing which we kind of tried to do, we wanted to have, transformers have a global attention, right? But we thought maybe it will be kind of beneficial to focus on local features or build local edges. So we tried different local attention layers. I don't know, we tried like approximately, 15 or 20 different local attention layers, but we had some issues. First of all, it was kind of relatively slow. At least our implementation. Maybe somebody much smarter can implement much faster. It was really taking a long time to train with them. And then what we decided to use GraphNet as a local kind of substitute for local attention. So pretty much what we did, we took your guys' baseline. There's few modification we did. First of all, the edges were built on not only on location of the sensor, but also on the time, XYZ, T. Then we substituted all activation to GLU, And we also got rid of batch norm and substituted to layer norm. If I remember correctly, GraphNet at the end does like 4 pooling, like mean, max, median, and sum, I believe. So we kind of got rid of them. So basically what happens is that after each layer after GraphNet, we basically have just one encoder layer, which will kind of matches the dimension of our encoder output. And then we just concatenate them and feed to the transformer. Yeah, okay.
It's my turn. So our transformer model consists of 4 layers or like 4 blocks with relative space-time bias, followed with 12 regular transformer blocks, which use the classification token concatenated with the input sequence, and the output of this classification token is used to produce the final model prediction. We consider 3 model sizes: tiny, which has approximately the same computational cost as the organizer's baseline and has 7.6 million parameters; small with 29 million parameters; and base model with 116 million parameters. Next slide. And as a training setup is rather standard for transformer models, we used Adam W optimizer trained for 4 to 5 epochs. We used all data, and the last 5 data batches were reserved for validation. The maximum sequence length in training is 192, and the validation is performed at the sequence layer length 512. The first epochs are done with von Mises-Fisher laws, and the last epochs we are using the competition metric as a loss with small additional term with loss Mises loss. It allowed us to get about 55 base point improvement. Next slide. So this table summarizes our finalized experiments and use of transformer instead of the graph neural net gives a 300 base point improvement over the baseline. Using the classification token or average pooling gives no significant difference, but we will using classification token to produce a final output. Also, we tried to run transformer without Fourier encoder, and we just projected the input variables to the transformer dimension. It gave 200 base point worse results. Scaling up the model from tiny to small and to base gives approximately 30 base points at each model size increase. Use of graph neural network encoder has contradictory results. In experiments we ran at the same hardware, we have approximately the same performance with and without using of this graph neural network. However, in experiments which ran at another hardware with 2 A6000 GPUs and larger batch size, we have better results. So these better results may be as a resulted by use of graph neural network or by a different batch size. Next slide. Our ensemble is a simple linear combination of 5 models, and the weights are computed based on a linear model fitted in the 5 random speed. The ensemble gives only a small improvement of our score in comparison with our best model. We also tried more complicated ensemble techniques, but without any significant improvement of the results. Could we go next slide? And out of the findings, I would like to mention the implicit leak. Specifically, the data in this competition is the result of computer simulation, and so the 0 time has a particular meaning. I expected maybe the time when the neutrino is added at the box boundary before the simulation. So the time of the first detection with respect to 0 may give an additional information such as approximate limitations of the track direction based on the traveling time from the boundary box to the detector. So the model can utilize this leak and get better results. And to verify this hypothesis, we ran an additional experiment where we subtract the time of the first detection from all detections. This experiment gave 145 base point worse results, so it confirms that our model is using this leak, similar to the organizer's baseline and similar to the majority of participants of the competition. Meanwhile, in real detector data, there is no such thing as zero-time reference, and the models may be expected to work worse on this data. And next slide. We performed some basic analysis of the model robustness. However, because of the time limitations, we will not go over it. And if you have any additional questions, we can discuss it in details.
Yeah, same thing. We can discuss this in error distribution also during the discussion. But we did pretty extensive analysis on our results. So the last point is simple model. Maxim, you want to finish with simple model?
Yes, sure. Our single T model which has comparable computational cost as the organizer's baseline, and which has 7.5 million parameters, can take top 5 in this competition as a single model. And our larger B model can take top 3 in the competition as a single model. So it is a quite exciting result.
Yeah, that's it. Thank you very much again for organizing, and we are really looking forward for your questions and discussion. Yeah.
Thank you. Let me stop recording.